Hello everyone, this is the solution to homework 2. Now, we had two questions here, and the first one was about the settling time and rise time of second order transfer functions. Now, we have a basic second order transfer function given here. The parameters are zeta and omega n. One of them is the damping ratio zeta, which is varying between 0 and 1. It could be greater than 1, but then we are talking about a different type of system, which is called overdamped systems. But here the restriction is between 0 and 1, which means that we will have underdamped systems. And if it's exactly equal to 1, it will be critical damped. If it's equal to 0, it will be undamped. So that's that. The omega n here is basically the natural frequency. If we increase it, the oscillation frequency will increase, etc., etc. So we can use zeta and omega n to define all the underdamped second-order transfer functions, which, as a matter of fact, have complex conjugate poles here. So, and the task is as follows. We have the settling time here. We know that the model is given as here, the model being the formula for the settling time. So we know that if we have the damping ratio and the natural frequency, we multiply them, take the inverse, and then there's also another coefficient which is not given here, but I know what the coefficient is, and we all know what the coefficient is. It is approximately 3.94. So this should be 4 divided by zeta times omega n. But, of course, we assume that we don't know it, and we're kind of investigating the system and the model and how we can acquire this result. How can we model something in a certain sense and try to come up with the coefficient and fit the model to it? So question 1 has two parts to it. One is the settling time, the other one is the rise time. In the settling time one, we have, again, two subparts here. One of them is the manual approach, which I'm going to do in a minute. And then there's also the semi-manual approach. We have a MATLAB fit function, which we can use. So we're going to use that. So let's start with a for loop approach here. So first of all, we know that we have basically a zeta and omega n parameter here. And there's also this mesh grid here. If you don't know what it is, help mesh grid. It will show you that it will create matrices for you so that it matches each zeta vector to omega n vector. So you will be able to just address the whole rectangular grid. Now we will use the 2D version here, of course, because we have two parameters. So what it essentially does is it has an x vector here and a y vector here. So the x-axis and the y-axis, we will have an interval. So the x-axis, for example, is zeta. The y-axis is omega n. We will have intervals for x and y, or zeta and omega n. And we will grid the whole region so that we will have individual points. We will use those points in order to calculate what the actual settling time is based on step info. And we also need a certain parameter vector. And this model, we will test this model, take the difference, take the square, sum it over the whole domain, and then come up with an integral squared error value for each parameter that we try in here. So we will try some parameters for this. But for each parameter, we will have a domain, and in that domain, we will calculate the difference, how good the model represents the actual settling time of the system. So let's first create this. Now, we know that zeta will be between 0 and 1. So let's create the zeta values here. And let's start with 0.1 with 0.1 steps up to 0.9. We can increase that, but I'm going to stick with that. So this is zeta. Zeta is basically the angle in phasor form, but we need also some radiuses because we're addressing the complex domain. We are on the S domain. We also need the omega n value. So omega n is a positive real number. So what we can do is we can just choose omega n val. Omega n val. equals 1 with 1 steps up to 100. We can again change that, but omega n can be 1, 2, 3, 4, up to 100. I'm just making up these vectors for now, and I'll see how good it will perform. Once we've done that, let's assume that the x-axis is basically this one here, and then we will have the y-axis here. So if we use mesh grid, it will give us a grid of zeta val and omega n val. So let me show you what it does. Let's call it run 1, run it again. So x. Now you can see that we have basically the same vector over and over again. You can see that the zeta val 0.1 up to 0.9, we have the same vector here. All the rows are the same vector. But here, all the columns are the same vector. And if we use a certain point, let's say the first row, first column, we will match 0.1 with 1. If we pick the next row, we will pick the next value. So you can see that it will associate each possible outcome to the 2D space, the domain. So let's also, by the way, get the row and the rows and columns. We can maybe use that, use the size function on any of the resulting matrices here. So now we have basically a grid. We will use it over and over again. But the issue here is the following. We need the settling time for a certain zeta and omega n value. So what we can do is, of course, we can use GS equals an NTF, and we can just use omega n squared and then 2 times zeta omega n squared. So this would be our transfer function. We would look for info equals step info and then use GS, and the TS value would be then info dot settling time, like this. But I don't want to repeat this over and over again. You might take this block of code and use this whenever it is needed. But a nice trick would be to define these as actual functions. You can open up a new script, define a function, give it a name, and copy paste it. Or you could also use the following approach, which I like sometimes to use, which would be basically get, let's call it getTS, which would be the MATLAB's lambda function, sort of, or function handle, where you can just use an @ sign, a parentheses, and then the expression. Now the limitation here is the following. When you use a lambda function like this, or a one-line function definition, your expression should also be a one-line expression. Here this block of code had 3 lines, but I might just reduce that if I take this and plug it in here. And furthermore, I can also get rid of this info by plugging it in like this. So I can basically use this one line, the step info of the transfer function, where we have omega n and zeta values like this, and dot settling time will only return the settling time of this. The only problem here is that what should be the function parameters? What am I going to change here? Well, one of them is going to be zeta. I will change the zeta value here, and the other one would be omega n. So this gives me the following possibility. So let me just run it here. If I run getTS, zeta equals, let's say, 0.5, and omega n equals 2. So zeta times omega n would be 1. 4 divided by 1 should be 4, so it should be approximately 4. And you can see it gives me the settling time 4. Now I can give some zeta omega n pairs to this function, and it will return me the settling time. What it does behind the scenes, it just defines the transfer function accordingly, because we have the formula given here, and sends it to step info and uses the struct here and gives me the settling time value. So basically this is a one-line code that I want to add. And furthermore, I'm also going to do something like TS formula here. And it basically needs almost the same. I want to provide a certain zeta value, a certain omega n value. And it should be something divided by zeta times omega n. So we could call this TSA or TS info or something like that, but yeah, let's stick with this naming. So I need a parameter here. Let's call it param. I don't know what the parameter is. And the parameter is this. So this is because I'm a little bit lazy. You don't really have to use this route here. But I like to do stuff like this for the moment. Now, yeah, what it does is it takes zeta and omega n and a certain coefficient or parameter. That is basically what I'm going to calculate. Yeah. So, the thing that is missing now is the following. We don't know in what interval we should basically look for this param here. We don't have a vector for it. So let's create a random param vector here and call it maybe from 1 up to 100 for some reason. Let's also have a objective vector. Now the thing is the following. For each parameter that is available in this param vector, I'm going to have an objective value or a value that represents the fitness function, sort of, or how good the parameter fits the model or represents the settling time. Therefore, I need a vector of the same size, which I'm going to fill in the for loop. So size param vec. There we go. Now, let's say we are choosing just one parameter here. So param val, param vec, 1. Let's choose the first one. I know what the parameter is. I can access TSF. So I'm going to do something like TSF zeta val, omega n val, and then I have also param val. So I know what this is. And I can also use get TS, but TS does not have any parameter at all. So this should be the actual settling time. This will be the settling time based on my formula here, param divided by zeta times omega n. I need their difference. So that would be it. I will take the square of this. And I am then going to calculate the sum of this. So I need to sum this over the domain. Now you can see that I have zeta val and omega n val, but I don't have them now. So when we have mesh grid, you can see that X, for example, on its own, is a 2D matrix, whereas Y is also a 2D matrix. So I also know what the rows and cols are. So for each parameter, I will have I from 1 to rows, and I will also have J from 1 to cols. And I will extract what zeta val for this instance should be is basically x I comma j. So if it's 1, 1, I'm getting 0.1 here. I'm going to do the same for omega n val, but it would be y. So here y would be then 1 here. So 0.1 and 1. So we need a sum here, and we're going to add this to the sum. So I've picked a parameter, I have a sum, I go through each row, each column, pick the right zeta value, pick the right omega n value, look for the difference between the formula with my parameter in it and the actual settling time. So now I'm adding them. I'm adding the square to it, and once I'm done with it, it should be basically somewhere here. I need to assign my objective value to my sum here. So the integral square error is basically the sum of squares and nothing else. Now, the only thing that is remaining here now, or if I run it, for example, for once, let's run one. Of course, I should have added this here. So objective, you can see everything is 0, but the first one is something like this, 1.979 times 10 to the power of 3. So I have to basically wrap it around another for loop where, let's say, k starts from 1 to length param vec. So now I'm doing this for each parameter value here. And I need to choose this based upon this, of course. Now, not the first one, the kth one. I'm doing the same here, not the first one, assign it to k. And what I can do is I can just create another figure here, maybe hold on and grid on. Plot the param vec against the objective here. With line width, let's have 2. So X label is going to be param, Y label is going to be objective. So let's run it. Now we have 100 entries here, 9 entries here. So the domain has 900 points. And for 100 different values, we're evaluating 900 points, which makes 9,000 points, I guess. So it takes quite some time. Yeah, let's see. By the way, I can actually go on with this. I'm looking for the minimum, so val comma index, the minimum of the objective, because the closer the model to the formula, or the formula to the model is, the lower the difference, the sum of squares difference will be. So therefore, the minimum, the better. The maximum, the more off it will be, basically. So I'm interested in this index, and the param vec index seems to be the param val that we are going to be interested in. So we could display something like this. The parameter is, and then string param val, maybe with integral square error, and that would be the value then. Something like this. Takes a little bit too much, so let me just drop it down to 20 to ease the pain. Let's see. Yeah, now hope that MATLAB catches up now. So, oh, yeah, well, doesn't matter. Um, Now this is doing it manually. Of course, I know what the exact value is, and I'm going to increase the accuracy in a moment. I can just shrink the param vector to a certain interval, but I want to see the whole picture here. But let me recap what we did. We defined a zeta vector, we defined an omega n vector, therefore we know the domain of interest. Ideally, omega n can be tending to infinity, and it could be very, very small values like 10 to the power of -6 around the origin. So it could be a good idea to take it logarithmically, maybe. That could be one adjustment that we can do. Zeta can stay linear because it is linear and it is limited. Therefore, we need to actually increase that. But if I increase something here, it would drastically increase the amount of points to check for just one parameter for this method here. So we've calculated the row and column size, so the domain, how many points on the x-axis, how many points on the y-axis there are. We've calculated that here. And then I defined a one-line function which gets rid of the crowding here. It just does the job here, and it separates kind of the code here a little bit, which is a good idea because I might test something else. I need to update these two functions, and it will use the sum of squares method here for a certain parameter. So it is a better code structure. Here we have a one-line settling time evaluation method, which is basically experimental results. It relies on step info, which plots the step response, looks for the settling time, and returns that. Where here we have a formula which should do the job if it's good enough. We are looking for the parameter value that is ideally the best value here. So, and then we have a vector. I have defined a vector and an according objective vector here. So I will be able to assess which parameter is the best based on the objective vector here. The lower the value in OBG, the better the param_vec value is. So then I took the parameter, defined a sum, we go use two for loops, go through each point in the domain, take the corresponding zeta and omega n values, plug them into these getTS, which gives me step info settling time, and this is basically if the parameter is the parameter that is chosen here, it takes the difference, the sum of squares, and puts it back into OBG. So once I'm done with it, I can plot it, and I can also go ahead and take the minimum of it and well display it here. It seems like 4 is a good value, and you can see that around here we have our optimal. So let me just change it here between 3 and 4 with 0.1. And we can also maybe update this to log space from -2, so 10 to the power of -2 up to 3 for, let's say, 80 points. I don't know why, but yeah. I'm sorry. What we can also do is we can also plot basically the param_val, comma value here, like this, to indicate that that's the best point. So let's see. Still takes some time, but this time around it should be a better runtime here, I guess. So Well, we know that it should be 3.91 or 3.8. In this case, if we increase the points here, we should get better results here. So yeah, we can see that this is basically the best point that we can get with this formula here. So this is the manual approach here. And if you want to be a little bit more fancy, what you can do is you can also show the domain here. We have used this domain with these points, etc. But yeah, I'm not going to go into detail here. Now, let's actually move on. We have done this part here. So let's use the MATLAB's fit function. How can we use that in order to solve this problem here? So again, we will have the same zeta and omega n values here. But for this case, let me just redefine them actually here, down here. So now we need to actually use the MATLAB fit function here. And for that, we will basically plug in some values. And we need to create a special table here so that we can keep track of stuff. Now here we will not use mesh grid at all. So instead of doing that, we will basically create a table. Let's call it params here. Now, for the params vector, what we want to do is we want to basically, sorry, we want to basically place the zeta value, the omega n value, the settling time value, the rise time value. So we will stack them row by row and provide this to the MATLAB's fit function here so that we can solve it, and it would look like the following. So basically if we plug in help fit here, we will have fit options, fit type, etc. We will have this pop-up here, and here in this pop-up we can see there are lots of different models to use, and it's basically trying to fit a curve or surface to data. So we need to create that data and then call fit here. And there are some restrictions, and the easiest way of summarizing the restrictions is that it would be a row by row basically matrix in this case, but then we will choose columns and provide some dependent and independent variables, and then just hope that MATLAB's fit function will take care of that. Now, the advantage in the fit function here is that it has many other theoretical aspects to it, so it will work way better than this manual approach, which checks each point. Even though if it's maybe not necessary, it will do some over calculation here. We want to get rid of that and have a better fit algorithm or program here, or fitting program here. So now we have zeta val and omega n val. We need to again loop through them. So basically it would be something like this here. This part will be repeated here. Let me just place this here. Now, usually I like to have static vectors or arrays, so I like to define it with zeros and predefine the size of that. But in this case, for the sake of simplicity, I'm going to skip that and I'm going to use a dynamic array allocation here. So MATLAB will grow or shrink as needed. I'm not going to bother with that. So we don't have rows and columns. We will have length omega n val and also length zeta val. So, and this should go here, I guess. Actually, this one here should go there. So omega n val, the ith element, and zeta val, the jth element. So at this point, we have two nested for loops, and we will have the zeta val here. So now we have some options here. So this is basically the actual settling time here. I'm not going to use TSF because I'm not going to tell MATLAB or use a function for that. I'm going to tell MATLAB the MATLAB's fit function, and it will just know how the formula or how the model is constructed here. So since we have getTS, what we might also need here, because in the second part we have the rise time here, we can copy the first line here and call it the getTR, the rise time here. So it will be the same, but the only thing is that it will start with rise here, so it will return me the rise time here. So we have the settling time, we have the the rise time here. So if we look close here, we see that we have zeta, we have omega n, ts, and tr. So we are going to create our, maybe we should call it tr here and ts here. So there we go. Now the params is going to grow. Params. Next row is going to be zeta, omega n. Actually, it's called zeta val. Omega n val. Yeah. And then settling time, and then rise time. And this should be our table here. So let me just quickly disable this. So let's run this. Oh, I need to copy the first part here. So there we go. Now, if you look at the params here, we have too many of them. So maybe params, the first 20 rows. So here we can see we start with zeta 0.1 and then omega n value 0.01, and then we get basically the settling time and rise time values here. And it just does it for the whole zeta vector for omega n fixed value, and then it goes on with the next zeta vector and omega n combination, and it goes on like that. So we will provide this whole thing as data in order to come up with the formula here. So let's actually create our fit. We have prepared our data. Let's create our fit type here. So with fit type, we need to basically tell MATLAB what we want to use here, or what our problem is. So we have help fit type. You can see there's an explanation. We can just use different versions here. The independent one is time. You can just give even a formula for it. There are many ways of defining it, but I'm going to stick with the basically this one here, where I tell individually which one is basically the parameter that I'm after. And yeah, so let's say that we are looking for a divided by x here, where the coefficients are basically only a, so we're looking for a, nothing else. The dependent parameter is z, which means that z is equal to ax, and the independent parameter will be x. So a is the coefficient, that will be the result here, and this will be x. So basically, if we define this, and if we see what it writes down, you can see that the model that we are using is a comma x, and it is basically a x like this. So yeah, what we can do is we can actually add y here, so like this, and use y like this as far as I remember. So let me just look at it, fit type. Now we can see it is basically our settling time formula here. So I did already define this, so you might also just provide this z to omega n param here for TSF, but you can see it's basically the same notation, and I did the same here. So the first value is actually zeta, so keep that in mind. And when we are using the fit function here, the nice thing about that is we will use the params here, and the first one is actually going to be the x value as far as I remember. So the second one would be y. So what we can do is we can basically give 1 and 2 here. The first two columns are zeta and omega n, and we want to fit the settling time, so that should be basically 3. And we provide the fit type here, and then a starting point, which you can read from the documentation. If I run this, let's see if I'm mistaken or not. So we've provided a lot of data, but it tries to fit it. And if we look at the result, we can see we have the result. So the first two parameters are basically x and y, and the first two columns are x and y. And the third column here is for settling time, so we provided the third column here. You might ask yourself, why did we prepare the rise time? Because another function call will give me the rise time formula. So that's basically the reason why I did this. I just combined settling time and rise time in a table, but I'm just picking the columns. X and Y is this. This is basically the result, and then the fit type, which I have defined here, and then start at 0. And it ended up being 3.79 for the settling time. It shows us the bounds here. It could be between this and this, but we have basically the coefficient 3.79. As far as I know, what we can do is we can use We can use res.a. So res.a. So it is a structure, so res.a plus divided by zeta times omega n. There we go. So this should give us also a little hint. So if you're trying it, you can just go ahead and use res.a. You will get the coefficient. And that's basically it. Now, you can see that it didn't take that much long, because of course this is just brute force. It's just taking each point, adding it to the sum of squares, and trying to minimize it on an interval. If you know the approximate value, you can just use this in order to refine your prediction. But of course, this method here, the fit function here, has lots of options, lots of algorithms to it, and it would be a better idea to use that. Now, we basically have also we're also ready for this part here, the second fit here. We have zeta omega n, and then 1 divided by omega n, or zeta squared divided by omega n, zeta divided by omega n, and 1 divided by omega n. So let's do the rise time bit 2. I already have basically the data available to me. I'm going to change this a little bit here. It would be a divided by, or a times x divided by y. X in this case is zeta here. And what I'm doing is I'm just dividing zeta into omega n, so x divided by y. And then there will be a b divided by y expression here. So a times x divided by y plus b divided by y is basically my model at this point. And the first two are basically, again, x and y. But now the next column, the last column here, is rise time, so tr, so 4. And since we have two coefficients, the starting point should also have two coefficients, but I'm just providing 0. I'm not even giving it a guess. And I guess we should be good to go. Once you have prepared your data, it seems like it is quite easy to use it for rise time. Now, this would be res a times zeta divided by omega n, and then plus string res b divided by omega n, I guess. So let's run it. We messed up this part here. Okay. Again. Oh, we didn't tell it that b is a coefficient here. There we go. Now, yeah. Maybe we should plug in something like times here. And yeah, it seems like it. So we can see that the rise time can be modeled using 2.13 times zeta plus 0.72 divided by, maybe I should change the notation a little bit, something times zeta plus, so res a plus zeta plus b, the whole thing divided by omega n. Seems a little bit better. Divided by. Yeah, and you can see we have basically calculated the coefficient of zeta and the coefficient of the constant term here. And you can see this is approximately the rise time when we want to use zeta and omega n. And of course, I can do it one more time where we have even another coefficient here. We're adding another coefficient here. This time around, we actually don't change this part, but we have 3 coefficients, so this should be 0, I guess. The only thing that changes is basically the formula itself. So it would be a times x squared divided by y plus b times x divided by y plus c divided by y. I'm kind of decomposing it into its terms. So, and that would be zeta squared plus times plus this times zeta, I guess. And then plus string res.c. Let me see. Res.c. I guess this should be it. Let's try it out in order to see. This plus sign is not necessary, but other than that, it seems like working. Yeah. Now we have 2.29 zeta squared minus 0.15 zeta plus 141 divided by omega n, and it models the rise time here. So this is basically question 1, and you were asked to create a report out of this. It should be fairly easy because you have basically you have to explain the fit types here, and you have to explain the data, and that's it for the MATLAB fit function. You might just provide a result here. But for the first part, the report is more important for this first part here because you can create these graphics here, and that is basically going to give you this one here, where's the optimal, and you might also want to maybe show the domain, and that's basically it. So let's transition into the second part where we had basically a task here. The second part here was to implement the given function which calculates the breaking points, the j omega crossings. The input argument is a transfer function object, so the function returns a struct that is already predefined. I gave you already the templates here, so we can just work with them directly in order to solve the question here. So let's start with converting actually GS into GSS, and here's also the notation here that we need to convert that. So let's call sims s. We can access the numerator by gs.numerator like this, and the denominator like this. Now let's display the denominator, for example, here, and call main. And you can see here we're calling it like this. Be aware that I didn't change anything here. because it assigns stuff here. Even though if it's not correct, it will assign stuff here. If I enter info, everything is equal to 0, but I can still debug in here without getting rid of anything. I can see that the denominator here is basically 1, 4, and 100 here. So we have the numerator and denominator. Now we need to calculate the order of the system, which is basically the length of the denominator minus 1. We have also the constant term here. And then we will have the numerator and denominator polynomials. We need to use the for loop here from 1 to length num or denom, then it doesn't really matter, length of numerator. So we're basically cycling through each coefficient here. And ns is equal to ns plus. Now I will take the ith element of the numerator. So the first one is the highest order term. So this would be s to the power of n. But as I increases, this should decrease, so minus I. But if, for example, I is equal to 1, I would start with n minus 1. I don't really want that, so I'm adding 1. So n minus 1 plus 1 will give me n. And this is basically it. So let's also convert it to ds and the denominator. And yeah, our transfer function then, GSS like this, could be defined like ns divided by ds. So I'm not sure if I run it like this. Yeah, this is basically the transfer function that we need to use here. Now we're interested in the breaking points, and it might surprise you, but it is quite easy to calculate the breaking points of a root locus of a transfer function. And the function is root locus info, so we're interested in basically root locus information. We're assuming that we are dealing with p-type controllers here. Yeah. If you look up the root locus, theory, you would see that, of course, we have basically the root locus equation here, which is 1 plus k times GSS equals 0. And instead of GSS, you might also think about ns divided by ds here. So this is basically the root locus equation here. And what we do in order to get the breaking points is that we need to find the k in terms of the remaining here. So what I mean by that is that if we multiply with ds, we will get ds plus k times ns. And if we send ds to the other side, we get minus ds. And if we leave k alone, work our way out, we get this expression here. And in the root locus theory, we know that if we take the derivative of k, so dk divided by ds equals 0, like this. If we solve this, then the points that will be calculated from this will be the candidates here. So, yeah. Therefore, we need to take the derivative of minus ds divided by ns. So, let's actually do that. I'm not even going to define the whole thing here. I just know that I need to define this fraction here, and I'm going to basically take the derivative of this. In the symbolic toolbox, we can use diff and temp, comma s. So comma s stands for the derivative respect to s. And basically, I'm going to equate this derivative to 0. And we need the solution here, solve. And let's see what's really going on here. So it seems like we have -2 in our case. So it would be a good idea to maybe change our transfer function into a more complex one. So let's go here. Let's leave that there. But let me just put in some values here. 1, 3, 4, 6, 3, 4, 1 times a very complex one. Just arbitrarily, by the way. I just want to... Yeah. Now, if we have such a complex transfer function, it is important to note that we end up in stuff like this. So we have to basically, first of all, convert it into double so that we don't get this messy stuff here. There we go. Now, first of all, what we have to do is the breaking points, it cannot be actually imaginary ones. So they should be basically real values. So we need to eliminate the imaginary values here, or the ones with imaginary values, like these ones here. So we can do that by checking the imaginary value of the solution here. If it's equal to 0, we're interested in it. If not, we're not. So basically, I'm going to plug this back into the solution. It will eliminate them. You can maybe define it as index equals the ones that have 0 imaginary parts, and then solution index. It's quite the same. It's called main. There we go. We have -3, -1.46, -259.47. So let's return the values here. So I'm going to assign basically this one here. And in the info, we get 3 doubles here, and info.bpoints will give us -3, -1.46, and -2.59. So let's actually also plot a root locus plot of this horrendous system here that I've picked. So let's hold on. And let's plot the b points here, info.bpoints, comma 0. Actually 0 times this, maybe, comma k squared line width. So there we go. Let's call main. Let's call it another time. Of course, we messed up this part here. So we get this here. Now, there we go. Now, this is a breaking point. It's quite obvious. This is also another one. it is on the root locus. The problem here might be about the ones that are not on the root locus. And for this, we need to eliminate the ones that are not on the root locus. And but there might be also another issue here. Let me just let's have a subplot here, a side-by-side one. So let's open that up. So we're interested in the root locus here, but here we're interested in the negative root locus. So now we can actually see that even though the one here seems to be not on the root locus, it is on the negative root locus here. So this is a very high order system here. Therefore, of course, there might be cases where it is not on the root locus, but generally it is on the root locus if you eliminate the imaginary parts in the breaking points, because the branch that is not on one of the locuses will be a branch on the other one. And if it's on the real axis, the whole real axis will basically complete itself. So what I mean by that is the following. Let's combine that. Let's give it a color of, let's say, blue. Let's give it a color of red and blue. I'm sorry. So, oh, let me, by the way, get rid of that. Hold on. So there we go. So you will see basically branches in red, branches in blue, but all the points that are kind of the candidate breaking points, if they're on the real axis, it is actually sufficient to say that they will be breaking points. Of course, we might also implement something like the following. We might want to be real sure if it's on the root locus or not. We might write the angle condition of root locus to eliminate if it's on the root locus or not. For that, we need to kind of, since we have GS here, I would recommend you to come on down here, maybe call it sol equals sol index here for now. And then we would just get the poles and the zeros, PZ map, GS. And then we would look for each point in the solution here, so that the, let's call it tests, it would be sol.I. We would get this one here, but then we would need to look for the vectors, and since they will be imaginary values, what I sometimes like to do is just use the point minus C poles. So let me show that to you. Yeah, of course. So let's comment this out. Let's call main. So at this point, these are the vectors that are drawn from the poles to the point on the real axis that we are interested in. And I guess there was something called angle D here. maybe angle, but now we've lost that, so let's call it vector here. Angle of vector. So you can see we have some angles, but we have to calculate times 180 divided by pi in order to convert it into degrees. So from each point, what is basically our destination point? Let me see. And what are the C poles, of course. Yeah, makes more sense now. So our poles are these. Our destination is -3. You can see this is on -3, this is on -3. So the distance becomes 0, but the angle seems to be interesting. What is the vector here? So main, of course. So the vector is 0. Oh, because of the negative sign, it's MATLAB. Okay. Yeah, 180 degrees is that because it seems to be complex conjugate pairs, or for some reason MATLAB decided to give it a thing like that. Maybe we want to let's get rid of that. Let's get rid of that. Maybe we want to was it round 2.2 to 1 digit? Yeah, maybe we want to round it to 1 digit, make 1 digit. I'm not sure if it's going to work. We'll see. Yeah, it's not really that important, but we got rid of that. Now we have the angles here. And the sum of these angles should give us basically the following here. So you can see it's 360. If it is basically, was it mod? So let me just get rid of that. So mod, help mod. So mod 380, 180 gives us 20, of course. So the mod of this value 180, if it's equal to 0, then we're interested in it. So basically, let's just, for one sample, let's just do it here. Oh, by the way, I need to add the angles from the poles, subtract the angles from the zeros. So basically, I'm extracting this here. So this will belong here somewhere. So this is, let's call temp equals the sum here. And then what we need to do is we just need to repeat this thing here for, we have that already, zeros, and then we look at the angle of them, and if I'm not mistaken, temp equals temp minus sum will be that, and then if temp is this, that would be basically it for this one here. So logical 1, so we get basically 1, 1, 1, 1. And if they're 1, we don't do anything. If they're not, then we will eliminate them. So checking the angle condition is quite easy. On the contrary, if you think it's complicated, because you have to know that this is a vector operation, you need to do the angles. There's a function called sum that takes care of the complex stuff here. So we could do something like, if this is equal to that, or else if this is equal to this, then solution I will be erased, I guess. But if we do that, we might go into trouble. Maybe we need to create a copy of it. So let's call sol2 equals sol. And we copied it. We just, if it's not 0, sol2 I should be basically erased. I guess this is the way of erasing it. And this should be sol2 here. Let's see. Yeah, it did nothing, of course, because they are on the root locus. So therefore, we didn't erase anything here. You can see we've copied this and we've assigned sol2. So if there's an erasure going on, it should go on here. Now, this is the first part. Of course, I would argue if this is necessary, but to be sure, you might do this. But the most important part here is that the imaginary parts ones should be deleted. And you should also know that the minus ds divided by ns derivative will give us the candidate points here. So if you want to be sure, you can just add this point. If you skip this part, it is okay, because overall, it is important that they should be real values. The candidate ones will give us also complex values, but we don't have any interest in them at all. So, what about j omega crossings? Now, this is a bit easier in this case, because we need to have a symbolic k variable, and we know that the closed loop, you can also use k times gs divided by 1 plus k times gs. Use num then on it and take pcs out of it, or you can also use k times ns plus ds, because it is basically the same. So I'm going to use sim omega real here, and I'm assuming the following. S equals j omega is one of the roots of the closed loop, and if that's the case, that's the stability bound. And at that point, we will have a j omega crossing. So I'm just plugging in the j omega axis into the polynomial. If it's satisfying it, the real part and the imaginary part, when s equals j omega is plugged in, should be equal to 0. And that point is the solution of the closed loop. So basically, I can use this, and I can substitute into PCS S1I times omega here. So this is S equals j omega. And at that point, I'm going to solve basically the real part of P omega should be equal to 0. Also, the imaginary part should be equal to 0. Because I'm plugging in a complex number, the result should also be a complex number. So I'm taking the real part and imaginary part and equate them to 0, because, well, it's a complex number. If it's equal to complex 0, it should have real part and imaginary part equal to 0. Otherwise, I would be mistaken here. So let's actually continue. Now, the real part is equal to 0, imaginary part is equal to 0. We have the solution. Let's see what it looks like. It's called main, I'm sorry. So, we have sol.k here and sol.omega here. There we go. Of course, we should maybe convert them into double. So k equals double and omega equals double. I'm just going to get rid of these here now. Of course, I'm not done, but we'll see. Now info.k, info.omega, and you can see omega has negative values. So we have to eliminate those values. If we have if omega is greater than or equal to 0, include it and do it for k2. But here the order is important. I have to first eliminate all the other vectors and then eliminate omega. If I mess up the order, it will mess up the results. So let's run main. Info dot omega, info dot k. There we go. We can see that that's basically it. Now, based upon this, we can also plot basically the omega values, for example. What we can do is we can use 0, comma, info dot omega value here. And of course, this should be basically times 0 here. And again, maybe ks here. And line width 2, I guess. So now we can see the j omega crossings here. We have both captured the j omega crossing here and 0 crossing here. If you use minus omega also, you can also put in a marker here, but I doubt that it is necessary. So here you can see we have the breaking points, we have the j omega crossings. So it's more about the theoretical aspect of the root locus than about coding, but of course the coding part has also its thing going on here. So if you submit a file that looks like this, even if you check this point or not, because there is no limitation on positive root locus or negative root locus. So if it's on the root locus, it is on the root locus. We don't really restrict it on the positive one. So yeah, therefore it works for both if you don't even check if it's on the root locus or not. Because we're on the real axis and the whole real axis is going to be covered by the root locus plot. So, hope that this was helpful to you. See you in the next videos.